It's our opportunity to share expertise with you on all different kinds of subjects through fall and spring semester. And we have visiting experts. Yay. They didn't bring a briefcase, but they brought knowledge. So this is Katie Haase. She's an associate professor of biology at Austin Peay State University in Clarksville, Tennessee. She got her bachelor's in wildlife biology at Unity College in Maine, master's in conservation biology at SUNY College of Environmental Science and Forestry, and her PhD in interdisciplinary ecology at the University of Florida. So please welcome Dr. Haase.
Thank you so much. Yeah. Thank you very much for having me. I'm really excited to be here. And I just kind of wanted to explain why I'm here from Tennessee. So my colleague, Jackie, and I have been trying to start a study away program for our students here in Ketchikan during the winter semester. So she'd be teaching mathematics and statistics. I'd be teaching winter ecology. And so we came here for a site visit to take a look at the town, looking at locations that we could potentially do some of our work, reaching out to partners. And so I'm really happy to have an opportunity to talk about some research that I'm kind of starting up. So this is a little bit different than what I normally work. So my background primarily focuses in thermal biology, so studying how temperature influences animal behavior, whether that's how they eat, how they move about the landscape, how they escape from predators, and other sorts of behavior. And I've studied, moose in New York, wolves in Yellowstone, manatees in Florida, bats across basically North America, and primarily what my lab does now is bat work with hibernation in Tennessee and other parts of the Southeast. But I had this amazing opportunity to go to the Galapagos last summer, working on sea lions and looking at their behavior in response to temperature. And it kind of sparked this idea of potentially looking at a latitudinal gradient of behavior with this species that does range from basically Ecuador all the way out to Alaska. So that's what I'm going to be talking about today. And I want to start by giving a shout out to my colleague, Dr. Madeline Geifer. She actually was the impetus to studying sea lions in the Galapagos. She is a geographer by trade, so she studies how human development influences the environment. Did most of her work in China, then sort of stumbled upon Galapagos, looking at human impacts on sea lions, and asked me to tag along because this is what I do. And we're kind of taking this project into this behavioral thermoregulation, but wouldn't have gotten the chance to do this without Dr. Geifer's help. So I wanted to give her a shout out at the very beginning. So today I'm going to talk to you about little very brief facts about California sea lions, then discussing differences between California sea lions in Alaska and the Galapagos, looking at how the landscape of these two areas is changing and how this might influence behavioral thermoregulation. And I will explain what the heck that means if you're not entirely sure. And then I'm briefly going to talk about our proposed research because we are in this sort of hypothesis generating phase. But I felt like it could be a really neat discussion to have this here where, we do have sea lions here in Alaska. And then, of course, finally ending with conservation implications because I am a conservation biologist at heart. So I wouldn't be an educator if I didn't discuss the difference between sea lions and seals. Because if you didn't know, sea lions are not seals, right? It's definitely, something that I think non-biologists, non-scientists don't actually realize that they're different. So sea lions, you've probably seen, of course, haul themselves out on land. They can walk around a little bit. They're the ones that you see at aquariums with the balls on their nose. They're the ones that are in the movies, right? And this is because their front flippers and their back flippers are a lot more mobile, so they actually can push themselves up and they can walk on land. Now, we call sea lions in the family of eared seals because they actually have an ear flap to their ear. So you actually do see their little pinnae, right? True seals are in a different family, and we don't see an ear flap. They do have ears, of course, but there's no flap there. These are a little bit more streamlined. Their front flippers are usually facing backwards. They can't bring their back flippers forward, so they can't actually walk as well as sea lions can, and so they're usually the ones that kind of bounce or flop around. I call them little sea sausages. And then the other non-seal sea lion component in pinnipeds, which are the order of seals and sea lions, are of course walruses. So we're going to be focusing on sea lions because they can actually come out of the water a little bit more easily. They can move around the landscape a little bit more easily compared to what we expect with seals. And we do see this really nice large range of the species across North America. So here's that range that I'm talking about. So this is for the California sea lion. Now this is not to be confused with the Steller sea lion, which is the one that is primarily really what you probably see in large aggregations in Alaska. That's a lot larger. But the California sea lion is here, and it's mainly found in Southeast Alaska. And of course you do have some crazy records of this particular species and the Aleutians. It's also found all the way across down into mid-Mexico and down into southern Mexico. They're very social. I'm sure you've seen them if you've gone on any boat around sea lions. They're very loud. When I was down the Galapagos, I could hear them in my hostel 4 blocks away from the ocean with my door and windows closed. They're extremely loud and they're extremely social. So it makes them a really unique study species because we can look at not just human impacts on what they use and temperature impacts on what beaches they use, but perhaps those social behaviors. There's just unlimited number of questions that they can provide for us. Notice how the Galapagos is not on this figure. So there could be, when I say could, be an endemic population in the Galapagos. So the reason I say could is that biologists aren't sure about anything and we argue a lot. And it's argued that this species could potentially be a subspecies, so subpopulation of the California sea lion. It could be a completely different species, and so they'll call it a sister species because they are very related. Just goes down to the genetics, and if your friend is a lumper or a splitter, as we call them in scientists. But if you don't know where the Galapagos are, they are this group of volcanic islands off the west of South America, and they're part of Ecuador. Now, most famously, the Galapagos are known because that's where Charles Darwin got his sort of start in trying to really dive into the theory of evolution through natural selection. So as an ecologist, it was pretty magical to go down to the Galapagos to kind of see what Darwin saw and to be in the same places that Darwin, was. And so we can, even though we can consider these the same species, we know that in very large ranging species, such as this one, and specifically mammals, you're still going to have variation in certain characteristics. And one of the main characteristics we tend to see change across latitudes is body size. And this makes a lot of intuitive sense if you're thinking about animals that live in really cold environments compared to animals that live in pretty warm environments. They're probably going to see differences in body size. So the particular subspecies or subpopulation of the Galapagos sea lion is going to be smaller than what you'd see up in Alaska. These species are also sexually dimorphic in body size, which means the males are significantly larger than the females, at least at full grown. So here we have a male, younger male in the Galapagos, and here we have males here in Alaska. We can tell they're males because they have this deflection of their forehead, or they actually have like what we call the zygomatic arch on their skull. So when they're mature, we can usually tell that they're a male because they are a lot larger. So Galapagos sea lions range from 110 pounds to about 880 in males. Their length is about 5 feet to 8 feet. While the California sea lions, the females are almost twice the size at minimum in the California compared to the Galapagos. Males are upwards of 950 pounds, and their lengths are longer, from 6 feet to about 9 feet long. So they are significantly larger, right? This makes sense. If you are a larger animal, you're not going to lose heat as fast because you actually have what we call a smaller surface area to volume ratio. So you have, more thermal inertia to hold on to that heat. So it makes sense that they'd be a lot larger up in these higher latitudes. And so, of course, this makes sense because of the environment that they live in. You all live in Alaska. You know that it can get pretty cold. Temperatures can be freezing. salt water freezes at a lower temperature than fresh water, so they could potentially be in water temperatures that are 0 degrees Celsius, 32 degrees Fahrenheit. And this leaves them with a risk of hypothermia if they're not careful about what they're doing in terms of spending too much time in these cold waters. And this might also have an impact on obtaining food resources if it's too cold for them to be out in these cooler environments. Compared to the Galapagos, where it's a lot warmer, right? We are at the equator. If you didn't know, the equator gets more solar radiation per square meter than the poles does, based on the fact it's a perpendicular ray from the sun versus it being spread over a larger area. So we have not just higher temperatures of around 85, 86 degrees Fahrenheit, but they also have a lot more solar radiation that they're exposed to. And therefore, this gives them that risk of hyperthermia, which is their body temperatures are going to be too warm than they should be. And because of high solar radiation, they also potentially could get dehydrated. And if you didn't know, the Galapagos are these volcanic islands. There's not a lot of fresh water, actually. Only one island has a natural source of fresh water, and that's it. The rest is all shipped in for humans. So gaining water can be actually sometimes difficult for these particular species. So this is just an example of most of the time for California sea lions, they're found out in more Seward is where you probably see them more often. Of course, this looks similar to the coast we have here in Ketchikan, where you have this sort of rocky coast and they can find places to haul themselves out of the water. May be limited in some areas, right? If they want to get out of the cold water and expose themselves to sunlight to warm up. And of course, the water is a little murkier. It's definitely a little cooler compared to the beautiful Galapagos, right? Where you got these beautiful sandy beaches. The water is right there. But what's interesting is right off the beaches, you have this volcanic rock. It's a little hard to see, but it's this very, very dark black rock. And what's really cool, and one of the things that caught my eye when I was down there, is that at night, many of the sea lions move to the rocks. And I noticed because these rocks are extremely dark, they absorb heat throughout the day, just like a blacktop does. And what that means is that it's going to emit it, right, just like a radiator. And as night falls, it does get a little chilly. I was actually surprised being down there in July how chilly it got. And so these animals potentially are moving to using these rocks as basically a radiator. It's mainly more comfortable for them. Not sure why. That's actually one of the questions that we're interested in looking at. And so not just the temperature and humidity in these areas are different, but the landscapes are different, right? So both, I would say, Southeast Alaska and the Galapagos are seeing rapid development and human influences. The Galapagos weren't settled really until the 1800s and weren't permanently really settled until the 1940s because the U.S. built an airport there to refuel during World War II. So since the 1940s, it became more of a tourism sort of drive to this area. So there's about 34,000 permanent residents currently in all of the Galapagos Islands. They actually prevent anyone from moving there that was not born there. So even if you're a native Ecuadorian, if you're born in the mainland, you can't actually move to the Galapagos. You can only live there if you were born there, or if you marry someone who was born there, or if you live there prior to this law coming in the 1990s. They get about $250,000 visitors per year, and 70% of their economy is tourism. So if you ever go down there, it's similar where you have sort of cruise ships, you have a lot of souvenir shops, a lot of restaurants, really great fish. It's kind of similar in that tourism is the driver of their economy. But because of that, you have this rapid population growth where individuals are moving from these rural highlands down to the coast and developing this coast, which could be, perhaps problematic to sea lions that need to haul themselves out on these rocks. And now you have this built up area. This is an example of a built-up area. This is 2 blocks away from the beach themselves, where the sea lions are actually persisting. My hostel is right around this corner, so I could literally hear them through my door. And what's interesting is that even though, we have these beaches, we have these rocky coasts, the sea lions don't care about humans at all. They pull themselves up onto the sidewalk. This is a male with his harem. Don't care where they hang out and take a nap. They will literally go anywhere. And you don't want to get too close because they can they will sort of bark at you. They don't want you coming near them. They tend to ignore humans. Dr. Geifer that I mentioned actually got bit by a Galapagos sea lion a couple of years ago, which is one of the reasons she asked me to come along as like a second person, just for safety in numbers. But they will kind of be aggressive if you get too close to them. You can't really see this, but this is, they also like their 4 p.m. margarita on the beach. So they have a lot of little fish shops on the beaches, and they'll come up and sit in the shade, and that's the key, right? These species probably overheating in the hot Ecuadorian sun, and they want to seek shade, but that's where humans go as well. So that sort of was the impetus of looking at this sort of behavioral thermoregulation with the impact of humans. And then at night, they'll pull themselves up onto these rocks. But a lot of them also, I always joke about the homeless population in the Galapagos, they really like park benches. Not sure why or even how they get themselves up there. I've never actually witnessed that. But you will walk through the piers and it's just there on every single park bench. It's really entertaining. And they do snore sometimes too. And their farts they smell pretty bad. So yeah, it's really, really cool to kind of be down there. And we can kind of compare and contrast this to the southeast Alaskan landscape that's also changing, right? So we know that we've had permanent human settlements here since early, at least 13,000 years ago. But in terms of colonial colonists that kind of came in the late 19th century, just sort of bring in more of that mining, fishing, and logging. There's about 3 times as many permanent residents in Southeast Alaska, but of course it's a lot larger land compared to the Galapagos. Tourism is about 5 times as much. I think this is because it's easier to get to Alaska than it is to the Galapagos. It's also in country for at least most U.S. people. So we know that tourism is part of the economy as well as fishing and logging. And so we do, again, see this development on these coastal areas. And that makes Alaska, just like the Galapagos, more, of course, impacted by things like climate change. And climate change will sort of have a vein throughout all of this. That's actually what got me really interested in thermobiology 20 something years ago. So a lot of my work is looks through that lens of trying to understand thermodynamics because of that lens of climate change. So we're going to see impacts like sea level rise, changing temperatures, changing ocean conditions, etc. And of course, here we have Ketchikan, but just to kind of compare that, we also see this sort of coastal development where there's going to be human and wildlife conflict between sea lions using these areas. I had a hard time finding photos of sea lions in Alaska because everything was kind of the stellar sea lion, but this is in California on the piers. So they also utilize human, components, right? They don't really care that much about humans and the fact that they will sort of aggregate in these areas, whether or not it's natural or replacement if their natural habitat has been potentially lost. As you can see here, they don't tend to care that much about human influences. Okay, so we know that there is impact of human development on specifically coastal development on most marine life. My interests lie at what's the impact of human development on how animals respond to issues of temperature. And with the idea and lens of climate change coming through, this is even more imperative to know that how these particular dynamics might change over time, and just giving us a baseline is extremely important. So I wanted to kind of take a step back and give you some terms. I'm an educator here. This is not going to be a quiz, I promise, but to understand why I'm interested in these things, I kind of want to talk about basic thermobiology. So sea lions are mammals, just like humans. So we have live birth, we have hair, we nurse our young, right? There's a lot of other characteristics of mammals, but those 3 are the ones that are unique to mammals, right? We're also endotherms, which means we produce our own internal heat source. Mammals and birds are endotherms. You can see turtles, fishes, amphibians, they don't produce their internal heat source. This is why if you have a fish or if you have a turtle, you have to have a light, right? Or even a heating pad under, if you have a desert amphibian or a desert snake or something, right? Because they're not actually producing enough heat to maintain a body temperature. They're also homeothermic, and I have a typo there, don't tell my students. They're homeothermic, which means they have a steady body temperature. We're the same way, right? Our body temperature is 98.6 degrees Fahrenheit. It is that way. Even 1 degree increase, we would consider that a low-grade fever. So as homeothermic endotherms, temperature, even though it may not impact us in the same way we would expect it to change body temperatures of lizards and snakes because they don't have that internal heat source, we are I think, a lot more sensitive to changes in temperature because we are used to having that single body temperature. This is the only figure on this only graph on this whole presentation, but to kind of understand why too hot or too cold temperatures are important, I got to give you some more technical knowledge, what we call the thermal neutral zone. So basically, endotherms create their internal heat source through metabolism. That's probably a fad word if you're interested in like fad diets, right? The low metabolism or increase your metabolism. But basically, we can measure that in just respiration. So if you ever see a Gatorade commercial with someone running on a treadmill with a respiration mask, they're measuring their metabolism. And as endotherms, we have a range of air temperatures or water temperatures, which we have on the x-axis here, where our metabolism, our respiration rate, our metabolic rate is pretty constant. This is basically saying we don't have to do anything to decrease our temperature or increase our temperature, right? If air temperatures start to get too warm, we tend to respond physiologically by sweating. So we know when temperatures are a little bit too hot for us, and this might vary based on individual, right? If you grew up in Alaska, you might start sweating at a lower temperature than someone who lived in Florida. And what happens is when air temperatures get to be beyond that point, your metabolism will go up because you need to use energy to sweat or to do pant if you have a dog, right? That's energetically costly. But your body temperature, which is up here, isn't going to change. It's going to be maintained. That's the whole point, is that your body is actually thermoregulating. It's dealing with that too warm temperature. But there's going to be a point that it's going to be too hot. Your body can't adjust any further. And what happens is that's when you get hyperthermic, where body temperatures are too hot and you start to have things like heat stress. We see the same thing on the other side, where temperatures get to be too cold. And once we pass that lower limit, your body's going to start to respond. Again, body temperature is going to be maintained. We do things like shivering, right? Our body's response to cold is shivering, and that's creating heat because it's muscles moving. And with that, you can see that body temperature is going to be maintained, and then it's going to get to the point that our body is just not going to be able to produce heat to keep our body temperatures the same. So we're going to now see hypothermia when you go into this sort of cold stress. All mammals have this curve. It looks a little different, of course, if you are a mammal that lives in very narrow environments versus very, very wide environments. Mammals that have very, very large ranges to their species, like the California sea lion, is probably going to have a pretty wide thermal neutral zone compared to species that are found only on one island. They might have a little bit more narrow because they're not used to fluctuations in their air temperature. And so this is then sort of sets up how we can look at how animals can adjust when it gets to be too hot or too cold. Sweating and panting, shivering are only the things that we do as humans, but there are a plethora of other activities that the animals do. And to understand sort of how you can lose heat or gain heat, I'm going to go into biophysics now. This stuff I get excited about, right? But this is just very basic stuff. So there's 4 ways that an animal can lose heat or gain heat. And we're just going to pretend we're going to be talking about losing heat with this nice fancy sea lion posing in the Galapagos. The first way is just radiation. If you live in a house that has a radiator, this is radiative heat, right? You have hot water that goes through the radiator and it's just emitting that heat into your room. I grew up in a house that was close to 200 years old and we had a radiator. So essentially this is just heat emitting from that object. Convection is, if you think about convective ovens, it's using a fan, right? So convection is just the loss of heat through a moving body. So this is wind or water. This is why it could be the same air temperature outside than maybe you have inside, but if you have a wind, it feels colder. That's why we have a wind chill, because what's happening is the air temperature isn't different, but we have convective cooling, so it feels a lot colder. The third one is conduction. This is just the transfer of heat from a solid body to a solid body. So a lot of times we don't see or really look at this in mammals because when they're, on 4 feet, there's not a lot of things touching each other. But if you have an animal like this who's laying on the ground, that's spending out that surface area that heat could be transferred. This is if you put your hand on a hot thing, your hand's going to get warm, versus if you put your hand on a cold stone, your hand is actually heating up that stone because the heat's going to move from a hot body to a cold body. And then finally, the most efficient way that heat can be lost is through evaporation. That's why as humans, we have evolved to sweat, because evaporative cooling loses a lot of heat. And this is just that transfer of water from a liquid to a gas, and that releases heat. So animals like the sea lion can go take a dip in the water and come out, and now it's covered with water. And then that process through evaporation, even though they're not sweating, is going to cool them down. So all of these processes are called thermoregulation. I promised I would talk about what behavioral thermoregulation is, right? So thermoregulation is just our body's processes to maintain that body temperature. This is to try to adjust, increasing heat loss or decreasing heat loss, increasing heat gains or decreasing heat gains. And we can do this through behavior, but there's also other adaptations, which are basically different traits that have evolved over time for the benefit of a species. And we tend to break down the adaptations into 3 different sort of subgroups. One is morphology. This is, body size, posture, all these things that can maybe increase heat loss by being a larger surface area or decreasing a heat loss by curling up and changing a posture, right? This is why we have the cat index. If your cat is spread out, we know it's really, really hot. But if they're curled up in a little ball, we know it's probably pretty cold. That posture is actually just changing that surface area, and that's a morphological adaptation. We also have physiology, so sweating. Sweating is it's a physiological process that your body does automatically. We can't control that. Shivering is another example of a physiological adaptation. There's also some really cool cellular things I'm not going to get into, but if you want to talk about, ventricles and vasodilation, there's some really cool physiology there. And then the stuff that I really like to study is behavior, because this is those things that those animals are doing on that small time scale, right? Morphology and physiology are usually things that have evolved for that species. But behavior can be individual. It can be changing based on the environmental temperature that hour of the day, right? So you could see different behaviors of the same individual over time. And this could be something that could be really informative. And so things like basking in the sun allows that animal to be exposed to temperature, or seeking shade, right? So these are behavioral modifications that allow species to thermoregulate. And so to kind of talk about sea lions and bringing it back, we have a bunch of different ways that these animals thermoregulate, whether it's through morphology, physiology, or behavior. So this is down in the tropics. The first thing they're going to do is they're going to go seek shade, right? We've already saw those photos of the sea lions hanging out at the bar. It's not because they want their margarita, it's because, or caipirinha is what you drink down in the Galapagos, but it's because that's reducing that actual radiation that they're absorbing from the sun. They can change their posture. So we have this scientific name for this behavior. It's called sharking it, where they stick up their pectoral fin. And as you can see here, the reason this young sea lion is doing that is that it's increasing the surface area, so it increases heat loss, but also it's exposing it to wind, and that can cool them down. We see them do this in the water, where they stick up their fin that's covered with water, so you not just have convective cooling, but you have evaporative cooling, right? So this is huge, and this is something that we'll probably spend a lot of time looking at, because you can just sit on the beach and observe these types of things. This is really common when species are starting to get overheated. They'll limit their physical activity, right? If you run around, you're going to get warm. If you don't move, you're going to probably cool down, right? So limiting physical activity, seeking shade, changing your posture, all these things can happen at the same time to increase that heat loss. Swimming in water is key, because water cools you down. Water is 25 times more conductive to heat than air is. This is why 70-degree water is a lot colder than 70-degree air, because it's literally sucking the heat from you. So for an animal that's overheating, you'll see these guys just like laying on the sand in the water as it comes in, because it's just, they don't have to expend any energy swimming, but it's consistently cooling them down with the evaporative cooling. And then physiologically speaking, these species don't have as much blubber as we see in species in Alaska, right? Blubber is a really great insulator, so is very, very thick fur, right? It prevents heat from being emitted into the environment. This is why mammals are endotherms, or why endotherms have fur. You know, we have, it's the chicken before the egg, but endothermy evolved and then fur evolved to allow that endothermy to persist. And we can compare this. Oh, here we go. Here we have postural changes. So this is an example of a beach in the Galapagos. We have all this shade under here, and a lot of times people are sitting under there, and they're not going to more than likely go where people are. But you can see they're kind of laying out. They're not curled up. They're laying out to increase that surface area. Sometimes they'll sit up like this and expose their neck. Not sure why. I have a thermal camera and I want to come in and see maybe there's some vascular structure that allows for more heat loss there. Not sure why, but it's kind of cool to kind of see them just like laying out. Here we have seeking shade. Just a little note here. This is a marine iguana. This is one of the species that Darwin studied, and he called them the imps of darkness. And when I saw that, I started crying because I'm a nerd, but I was just like, because they're kind of, there's really cool variation with them across other different islands. So you can see they're not like touching each other that much. This is a pup. So the pups, of course, are going to probably lose heat a lot faster. And then maybe they actually could have issues with being too cold, but they tend to seek that shade. And we can compare this to the Arctic, right? We'd expect to see the exact opposite in behaviors, at least during the winter, where they're going to be more clustered. We have, again, scientific terms call it cuddling, but they're going to be more clustered. Keeping that heat together prevents more heat being lost. They're going to bask out in sunlight, absorb that solar radiation. They have a lot more thick blubber. They have a lot more dense fur. It really keeps that heat internal the body compared to, losing it. And across mammal species, we can also look at blubber and density of fur on the altitudinal gradients. But we're not going to be harvesting any animals to do that work, so that's going to be a little harder to do. And then there's other physiological adaptations to cold vascular structures, but I'm not going to get into the technicality of that. So these are behaviors that these animals are doing, and we can quantify them. And we also can quantify how might human impacts influence how good they are at thermoregulating. With coastal development, they might be losing those shade locations or basking locations. We're going to have some heightened human-wildlife conflict, which is what we call when there's a conflict of resources between humans and wildlife, because when humans are using shade sites because it's hot and you get a lot of sun down there, then of course that's going to disrupt the availability of these shade sites to these sea lions. And then, of course, with climate change, that's gonna, we don't even, it's so complicated that we can, try to predict what might happen with simple, okay, temperatures increase, but we might see increased storms, we might see a loss of food resources. There's a whole plethora of things that potentially could disrupt these areas. And so when I was down in the Galapagos, sitting on the beach, just watching these sea lions, we came up with a bunch of different questions. We came up with like 10 different things that we could look at, but these are 2 that are relevant to kind of Alaska. So I kind of want to very briefly talk about them and how we can actually address them. And the whole, point of doing science is to kind of observe, create hypotheses, figure out how we can test those hypotheses, and then go ask someone for money to go and do that, because science is expensive. And so Dr. Geifer and I have been sitting down and writing this out, and I just got tenure, so now I can take the time to actually write another grant, because prior to tenure there's a lot of other things going on. So these are 2 questions that we could potentially ask, and we will ask. I just don't know when. It depends on money, right? And both of them are going to be looking at this sort of latitudinal gradient. So from the pole of the Arctic down to the equator, of how these animals could potentially be altering their behavior. So the first is just the stuff that I love, looking at thermoregulatory behavior, right? So we can sit and we can observe these individuals using cameras, and my grad students who have been begging me to take them down to places like the Galapagos and to Alaska, and we can look at these fine scale postural changes, and we can measure air temperature, we can put up a weather station basically, and look at how these behaviors might change in the morning, late afternoon, dusk, night, when you have different environmental conditions. And these are things like using the water, so spending time in the water versus on land, sharking it, hanging out. This is the example of the one, it's literally laying in the sand, not expending any energy, and getting that evaporative cooling. Doing these postural changes where they're facing the sun and just kind of sitting there. Versus things like this. We saw a lot of individuals cover themselves in sand. And not sure why. I think, because I always think everything has to do with thermal biology, but just like the dark surface absorbs solar radiation, light surfaces reflect it. So perhaps they're using it to reflect solar radiation or add a sunscreen, not really sure, but we can measure those things. We can go out with a solar radiation meter and actually measure the reflectivity of it and measure perhaps how much heat is potentially being absorbed. And then we can look at the proportion of these different behaviors to these environmental conditions across that latitudinal gradient. So doing this in the Galapagos, someplace in California, maybe San Diego and San Francisco, all the way up to probably more like Seward, to look at these proportions of a behavior compared to these environmental conditions, and then look at the influence of humans. There are some beaches in the Galapagos where humans cannot use, so we can perhaps do a comparative study at the same exact day in the same environmental conditions of how these animals might be altering their behavior because of human influence, and then say, okay, if they need access to shade, if they need access to water, how might coastal development influence that type of behavior? That's really important to their survival, because if you don't thermoregulate and you go hyperthermic or hypothermic, that's not really great for the individual. The second one is clustering behavior. So as I mentioned, we see clustering in these species. They are very gregarious. They do have harems, and they kind of have social groups where you'll have like 2 or 3 harems on top of each other, and you know that they're separate because there's different males and they're just consistently screaming at each other, and then they'll fight each other. So you know that there's these social groups. And we want to look at, using drones, because it can be kind of overwhelming to try to count individuals. And this is not Alaska. You saw that Alaska picture. That's going to be even more difficult. But using drones to take imagery at different times of the day to look at clustering behavior, because there's some really cool spatial statistics that we can do looking at how these animals are clustering. Are they touching each other? Are they more spaced out evenly? Are they on top of each other? How does that work? And then we can relate this to human densities as well as those environmental conditions. Are they changing their clustering behavior based on the time of day, based on temperature, based on sunlight, precipitation, or are they changing them because humans are there? And we already see this. So here we have around dusk, which is a lot later than it is here, at least at this time of year, where the sea lions are kind of clustered. So it's getting a little cooler. So they're spending, not as many of them are spending time in the water. What's really cool is they actually have, I don't know if there's a picture of it here. Most of the Galapagos beaches, at least where I was in San Cristobal, have rangers that will yell at humans if they're getting too close to sea lions, which is pretty cool. And this is compared to in the morning when there's no humans. And you can see they're it's hard to see from the angle, but they are a lot more tight-knit when humans are there compared to when they're not. So whether this is a time of day effect or a human effect, we can actually ask that with fancy statistics, right? So we can look at these types of things using drone imagery. And the reason I want to use drones is that we can have someone in the Galapagos all year round do this, and someone up here do this all year round, rather than relying on me or a grad student coming up for a couple weeks. And then we can do those spatial statistics looking at sort of these stationary images. Is a lot easier to count than trying to do it. We try to do it in the Galapagos, and it's hard when they're moving around, right? And so this is extremely important because, as I mentioned multiple times, understanding how a species interacts with just thermal environment at its baseline is extremely important for us to predict what's going to happen to these species if, not if, when things start and continue to change. Some species are really adaptable. They're really able to acclimatize, they're able to change their behavior, and they're able to deal with it. Some species are not. Perhaps the sea lions, because they have this widespread range, have that propensity to be able to handle a variation in temperature. And this can also help us inform management practices, which I think is imperative to any research we do. As a scientist, I like to just ask questions to ask questions, but it's better monetarily speaking for us to be able to give management information to say, hey, we need to, perhaps prevent humans from using shade areas in the summers in the Galapagos, or perhaps reduce coastal development in these important areas to allow these sea lions to haul themselves out in the winter to warm up, right? And this potentially then could give us some broader implications of just marine mammal conservation in in this facet of climate change. So with that, I'll say thank you for letting me kind of talk at you. And I always like to give my information because I was a young child once, and if you all have any kiddos that are interested in conservation science or wildlife science, I'm always really happy to talk to them about how I got to be where I was, because I grew up in suburbs of New Jersey, had no idea what wildlife biology was. I knew that's what I wanted to be, didn't know that's what it was called until I went to a college fair and my university was there, and I was like, oh, wildlife biology. I knew there was a name for it. So that was kind of free Google. So I'm always happy to talk to people about that if anyone has kiddos interested in that. And so with that, we can take some questions. Yes.
I know you had talked, I think, on the KRBD interview, you had talked about tracking devices. What are you thinking about?
Yeah. So in an ideal world, I would tag everything. So most of what I've done in the past, most of my research that I work on is with tracking individuals. But the reason I didn't include that in this is because the likelihood of us getting permission to tag sea lions in the Galapagos is probably a little, may not happen. And so we try to, and it's also a lot more expensive to get those tags. They vary, they can be upwards of $5,000 to $10,000 depending on the tag. And marine animals can be difficult to track because once they go below the surface, depending on the signal strength, you'll lose data. Like it won't be sending it to any satellite. So I would love to be able to track them. We put tracking devices on marine mammals by usually pasting them to their back and eventually they'll fall off. And that could give us a lot more fine scale detail with certain individuals rather than relying on us to go and observe them. That can give us every hour of the day data, allow us a larger scale information about, we can't necessarily get the postural behavior from that. We can't tell if they're sharking it or not, but we can tell if they're in the water, if they're on land, what beaches they're on, are they actually moving in the water, and perhaps get a more broad scale information about what they're using. And that is one of the questions that we're interested in. And when we get down to actually, working with the Galapagos, I chatted with a Galapagos sea lion biologist, and he seemed interested, but it was not as excitable as the others. So I kind of have to read between the lines. And the likelihood of us being able to tag as many animals as we would need to make it statistically sound, I'm not sure about that, unfortunately. Yes.
How similar are stellar sea lions and California sea lions? I've never seen California sea lions up here. Is it mostly a size difference, or are there behavioral differences as well?
I don't think there's that much of a behavioral difference. They don't have as long as a range. They're mostly, stellar sea lions are mostly found up in these colder areas because they are a lot bigger. So they're going to be found in the coastal areas. They are, I think, a lot more gregarious in terms of the numbers. You tend to see, like, most of the figures, if you search like sea lions Alaska, are stellar sea lions. And you can usually tell just by the males are just massive. I don't know that much about in terms of the behavior, but I would make an assumption that they're probably not different. But I can't speak too much about stellar sea lions in that aspect. But they are gregarious. They have harems. They are bigger, but I don't know in terms of thermoregulatory behavior.
Would your research up here look at stellar sea lions, or
I'd love
are you
to.
only doing?
Yeah, I mean, it just depends on, it comes down to funding. And I'm always one of those people that if we're up here, might as well collect some data if we can. And especially observations, once we're here, it's free. Well, time, but we're already doing it, right? So I would love to do a comparative study between the species as well, especially if there's a big body size difference. That would be really, really interesting. Other questions? Yes, Mike.
Have there been any efforts to actually determine whether the Galapagos population is a distinct population segment?
Yes, and they argue. They've looked at genetics, and so if you look at it now, what I see most people looking at it is a separate species, but recent literature also includes it as a subspecies. So it's one of those yes answers that genetically they are different, but I don't know if it will be different enough for us to it'll be something that, like, in terms of behaviorally, I don't think the genetic component will be there. It's more of it was a founding effect, bottleneck effect, right? So isolated that component versus they're not different in terms of they came from different ancestors. It was more of like a potential splitting off because of this endemic population.
Can you talk a little bit about the program you'll think you're bringing here?
Yeah, so Dr. Vogel, it was actually her idea to do it because her daughter lives in Ketchikan. So and then there's some interest in looking at mathematics here in Alaska, and she asked me if I would love to join because I was just up here last year for a conference and trying to figure this stuff out. And so her class would be liberal arts mathematics, intro to statistics, and
maybe high impact practice
math education.
for math
Yeah.
education.
And mine would be more of like a wildlife ecology. So, excuse me, winter ecology. So specifically looking at how animals persist in cold environments, specifically in the winter. So looking at adaptations like migrations, hibernation, a lot of thermal biology, looking at physical, insulation, all those different examples as we compare looking at species here versus other areas. And then I always like to underline my classes with field techniques. So techniques that the students can learn, they'll actually use for a job. So we'd be doing like small mammal, live trapping, using camera traps, techniques that we use every day in the field, tracking and things. So it would be a very hands-on class for my students being out in the national forest and doing this work. So most of the students will be our Austin Peay students and then bringing them up during the winter master course.
Thank you.
Yeah. Great. Wonderful. Thank you.
Thank you.